Hi folks, today we're going to talk about scientific measurement. Specifically, we're going to be talking about sig figs. Alright, so let me stop right here and tell you, you need to get paper. You need to write notes on this one. This is a critical unit. You're going to be seeing significant figures, significant digits the entire year. So pause the video right now, get your pencil and paper. You're going to be taking a lot of notes in this podcast. Okay, the first thing is that whenever you measure something, it's going to be uncertain. So when I take a ruler and I measure something, that measurement isn't exactly perfect, is it? So when you take a measurement using a manual instrument like a ruler, you write down all of the digits an instrument gives you plus one uncertain digit, then you estimate. It's a lot easier to demonstrate that than to memorize that rule. Right? Now when you use an electronic measuring instrument, the machine does this for you. It guesses at the last number. It's not perfect. Alright, so let's look at a measurement. If I had a ruler that had numbers on it like this, each one of these lines, this line here represents 6, this line here represents 7, this line here 8, and this line 9. You'll see that I have ones all the way. Each one of these lines represents a 1. So if I had a pencil and it came out to here, I realize that's a lousy pencil, right? There's your eraser on the end. Okay, so the question is, how long is this thing? Well, it goes right to about here, right? So if this is 10, this must be 11, and this must be 12. Would you say then that this is maybe, this is 11 and 12. Wouldn't you then say that would maybe be 11.5? I would, right? Now the point here is that the lines tell you there are lines at 10 and 11 and 12 and 13, and you're going to go one more digit and estimate one more digit, which is this 0.5 business. Now, you might have said 11.3, or let's say I had something that came out to right there, and you said, well, that's 14. Well, no, it's not, because you have to estimate one more digit, so it's going to be 14.0. Might have been 14.1 or 13.9, but you're estimating at 14.0. You are guessing at or estimating that last digit. Okay, that's important. So let's say we come over here. Well, now we have 1 and we have 2, and each one of these lines you see is 0.1. So this is 1.1 and 1.2, etc. So again, let's say I have something come out to here, right? I'm going to estimate that's right there. So maybe that's 1.1, 1.2, 1.3. So maybe that's about 1.2. Let's write it up here. Maybe this is 1.28, maybe 1.29. I don't think it's as far as 1.30, but if I did have something that came out here all the way to right there, and I'm sorry, this is hard to draw, but let's say it came right down above this guy, right, then I would think it was 1.9. In fact, I would think it is 1.90, because I have to go and estimate that last digit. Right? So make sure, in this case up here, you're going to have one digit after a decimal point because that's what you're estimating. But here you're going to have two digits after a decimal point. And down here, you'll notice we have a line for 100 and a line for 110 and a line for 120. So again, you're going to estimate, and that might be 125, maybe 126, maybe 124. I don't know. But if it goes straight out to there, that's going to be 170. Right? And the problem is somehow I have to indicate that this 0 is real, and we'll talk about that in a minute. One way to do it is put a line over it. That's a way to indicate that it is real. Another way to indicate that it's real is to put a decimal point after it. And we're going to find out about that in just a minute. So, bottom line is you must estimate that last digit. So, here you have a meter stick. This silver thing is a meter stick. It goes all the way out to 1 meter. It's out here to 1 meter. So how long is this piece of wood? Well, it's about 0.6 meters. It's less than a meter. It's not 1 meter. It's not 0 meters. So it's a little bit more than half, which is probably right about there. So we're going to call it 0.6 meters. We're not calling it 0.65 meters or 0.61 meters. We're calling it 0.6 meters. One digit after the decimal point. Now here you'll notice I have something that's I have 0.6 meters and 0.7 meters. So now all of a sudden I can estimate where it is and say, well, that's at about 61 centimeters or 0.61 meters. Because now I have additional lines that help me out. Now, if I take that same piece of wood and put it in here where I actually have lines at 61 and 62, well, now I have to estimate one more digit. So it's somewhere between, 60 centimeters and 61 centimeters, which is 0.60 and 0.61, so it's somewhere in the middle, and so whoever measured it said it was 0.607 meters. If this is confusing, replay the podcast. If that doesn't help, come see me. Okay, we'll work it out together. All right, so why are measurements uncertain? Well, you just saw why they were uncertain. You're estimating that last digit. And also, instruments are never perfect. We don't have any perfect instruments out there. They're all mechanical, and so they are just a little bit off. All right. Have you ever gone into Walmart and looked at a bunch of different thermometers at the same time and seen what they read? They don't all read the same thing. Okay. So instruments always involve some estimation. If it's a digital scale or something, it's estimating the final digit. If you're looking at a ruler, then you're estimating the last digit. All right, so let's talk about reliability in measurement. What's reliability? Well, precision, we have two words. One of them is accuracy, one's precision. Precision says you get the same result over and over and over again under the same condition. So if I stand on my scale in the morning and it says I weigh 200 pounds, if I get on it again tomorrow, it says 200 pounds, and I get on it again and again and again, that tells me it's precise. It's giving me the same answer over and over and over and over again. Okay? That's what precision means. Accuracy, on the other hand, says you're getting close to what you expect to get. Right? Now, is 200 right? I have absolutely no clue. All right? But that's the number. If that number keeps coming up over and over and over and over again, it's precise. The question is, if I really weigh 210, or if I really weigh 190, then that number is not accurate. Okay? But it is precise, because it keeps giving me the same answer over and over and over again. Right? So, if I get on my bathroom scale at home, I care about something, whereas I care about something else if I'm weighing luggage. For example, on my bathroom scale, I really don't care whether I weigh 200 or 190 or 210. It really doesn't matter. I want to know where I'm going from day to day. Am I going up or am I going down? Okay, because I don't want to go up. I'm already up high enough. I want to go down. Right? But how about luggage? Well, you need to know exactly how much it weighs, because when you fly, they weigh your luggage. And if it's over a certain amount, they're going to charge you for it. Okay? So there, it has to be correct. It has to be an accurate number. Whereas the bathroom scale, I really want to know from day to day whether it's going up or going down. And that's really what I care about more. So if I look at these three arrows, are they precise? Or are they accurate? Or both? Or neither? Pause the podcast, see if you can figure it out. All right. These three are all grouped closely together. Now, were they supposed to be? No, but they are grouped closely together. They're not where they're supposed to be. Right? These things are precise, but they're not accurate because they're not next to the correct thing. So they have high precision and they have low accuracy. How about these? Well, these are far more, oops, you try it. Okay? These are far more accurate because they're close to the center, but they're further apart, so they're not as precise. So they're more accurate, but they're less precise. Okay. And, of course, what you'd really like to have is something like this, where they're grouped tightly together, and that's precise, and they hit the bullseye, which means they are accurate. All right. You try some with some numbers. Again, pause the podcast, see what you think. All right. These first three numbers that you see are all grouped very closely together. But they're not near your answer. These are precise. They are not accurate. These numbers are not grouped anywhere close together. So they are definitely not precise at all. Are they accurate? Not very. I'd say they aren't very accurate and they're not very precise at all. Now these numbers, those are all precise. They're all close together. But again, now over here they're trying to get to 9.65. They are not at all accurate. Right? Now, this first set was far more accurate than the third set. but they're still not accurate. Okay. Switching gears, we're going to significant figures. You better be taking notes on this part, folks. All right. How much money do you have in your purse? Well, do you actually say you have $4.72? I probably say I have $4, maybe $5, but I don't bother counting all the change. Sometimes we estimate. Sometimes we have to estimate. Sometimes we know an answer more accurately than others. For example, how many people are there in the United States? There's no way we can have that number down to the last one. It is impossible. Because by the time you count them, there are more that have been born. So that doesn't work. How old are you? Well, do you say I'm 16? I'm 17? Do you say I'm 16 days, I'm 16 years, and 3 months, and 4 days, and 2 hours, and 36 minutes, and 15 seconds? No, you don't do that. Right? You simply just say I'm 16, or I'm 17. So you're estimating. What time is it? You typically don't say it is 9:52 and 47 seconds. You typically just say it's about 9:50. So we're estimating. So what are our rules for significant digits? We do this because we estimate. We have to know, what did we really mean when we estimated? How far did we estimate? That's what we're trying to figure out. So when you have your rules for significant figures, you count all of your non-zero digits. So for example, if I have a number 1, 2, 3, 4, it is going to have 4 significant figures or 4 significant digits because they're all not zeros. Now if there's zeros in the middle, I always count them. So for example, if I have the number 708, the 0 is surrounded by a 7 and an 8. So you count it. So you have 3 significant digits. Those are the easy ones. Okay? 1008 has 4 sig figs. All right. If a number is less than 1, you count all the numbers after and including the first non-zero number. You do not count zeros to the left. You never count zeros to the left. You count zeros to the right if there's a decimal point. All right, so let's look at this. Here we have the number 0.000987. The 3 digits to the front are not significant. Now, guys, they are important, but they're not significant. Significant digits are over here on the right, the 987. So you only count zeros after a non-zero number. You never count them before. So you'll notice here I have an extra 0 on the right. So here my 987 plus the 0. The 0 is now a significant figure. What does that 0 imply? Well, it implies when we were measuring, we actually measured out to that particular spot. And that's why it's significant when we're talking about measurements. 0.9 has 1 significant figure. And if I look at 0.09, how many sig figs does it have? Pause the video, see if you can figure it out. All right, be careful, because leading zeros never count. And zeros only count if they're after a non-zero digit. So this has 1 sig fig, just like the one above it. How about that one? Same thing, 1 sig fig. And as we look at all of these numbers, you'll notice that the leading zeros, we never count them as significant digits. The only significant digit we have here is the 9. So each one of these numbers has 1 significant figure. If a number greater than 0 is a number greater than 0 and there's no decimal point, get that? And there's no decimal point, then you count only the non-zero digits and the zeros in between. You do not count the trailing zeros. Okay? You ignore trailing zeros. So an example, 48,000 has 2 significant figures. You say, wait a minute, if I take those zeros away, I've only got 48. That's true. I didn't say they weren't important. What it means is you didn't measure them. Okay? That's what it means. 408,000 has 3 significant digits. Why? Because it says you didn't measure those last 3 zeros. Right? These zeros here and these zeros here, you didn't measure. Now, if you had 48,001, then that says, yeah, I really measured it. But we're assuming that these digits, you never measured. They're just placeholders. So number 9, 90, 900, They all only have one significant figure, which in every case is the 9. All of the zeros are placeholders, but we did not measure them, so they're not called significant digits. They are important, but not significant. All right? So that's what this says here. Never confuse significant with important. 9 and whatever that is, 9 million, may have the same number of significant digits or sig figs, but there's a huge difference between the two numbers. If a number is greater than or equal to 1 and a decimal point is written, you count all the digits. All right, so all of your trailing zeros are going to count. If you look at this number, clearly it has 7 sig figs. But 1000.000 also has 3 sig figs. Right? And it is because there's a decimal point written, and where this implies that all of these digits we actually measured. Whereas down here, there is no decimal point written, so it only has 1 sig fig. But look at the 9 million down below it. Because we have a decimal point down here at the end, that implies that we actually did measure that 0. So that would have 7 sig figs. All right, that's a lot of rules. So I'm going to give you a trick to do it so that you can avoid all these rules. We have an Atlantic and a Pacific rule. Now, you should know that the Pacific Ocean is on the left-hand side of the United States. And Pacific starts with the letter P, and the word present starts with the letter P. So if I have a number that has a decimal point that's present, let me give you one. Let me give you a couple. Let's try 0.00390. What this says is I start on the Pacific side, which is the left-hand side of this number, and I find the first non-zero digit, which is a 3, and I count all the way to my other ocean, which is my Atlantic Ocean, and that tells me that I have 1, 2, 3 significant digits in this number. And that's correct. Right? If I have a decimal point in the number, even if it is 30,000, 30.00, this is going to have 4 sig figs. The zeros count because there's a decimal point. I start on the Pacific side, I find the 3, and I count all the way to my other ocean. There are a total of 4 significant digits here, and 3 in this number. Now, how about if my decimal point is absent? Notice Atlantic and absent both start with A. Well, in this case, I start on the Atlantic side, and I again find the first non-zero digit, and I count my way all the way to the other ocean. So, let's try another number. Let's try the number 39,000. Well, there's no decimal point, so we start on the Atlantic side. We find our first non-zero digit, which is the 9, and we continue counting to the other ocean. That gives us 2 sig figs here. Okay. Let's again write another number that let's say 4010. Again, we start on the Atlantic side. We find the first non-zero digit, and we count every digit all the way to the other ocean. You'll notice the fact that there's a 0 there. We don't care. It's a digit. All right. So here we're going to have 3 sig figs. So that's your trick. So I want you to try some. I didn't mean to put the answers up. Sorry. Right, I'm going to do these one at a time. Pause the video, and then come back and get back with me after each one. Okay? The 6903, there is no decimal point. It's absent. So I start on the Atlantic side. I find the first non-zero digit, and I count. That's a total of 4 sig figs. That's not going to work, is it? All right. Here my decimal point is present. So I start on the Pacific side. So I start on this side. I find the 5. I count all the way to the other ocean, and again, there are 4 sig figs present. Now, the same rule applies. Here I have a decimal point, so I start on the Pacific side. I find the first non-zero digit, which is a 5, and there are 3 sig figs present. How about this one? This one, I start on the Atlantic side because the decimal point is absent. I find the first non-zero digit, which in my case is going to be the 6. And I keep counting to the other ocean. This is only going to have 2. How about this one? Again, pause the video, do it yourself. Okay? Decimal point is present, so we start on the left. The Pacific side, we count to the opposite ocean, 4. How about this one? Ooh, don't get confused. The decimal point is present, Since decimal point is present, we start on the Pacific side. We start over on this side. We find the first non-zero digit, which is the 4, and we count every digit all the way to the other side. We don't have to worry about this trailing, leading 0 stuff. Right? We just count them, and that's a total of 6. How about this one? Decimal point is absent, so we start on the Atlantic side. We find the first non-zero digit, and we count the opposite ocean. There are 3. I think this is the last one. See if you can do it. Decimal point is present. We start on the Pacific side. When we start on the Pacific side, we find the first non-zero digit. First non-zero digit is the 4. So we keep counting over to the right. 4, 3, 0, 1, 0. That's a total of 5 sig figs. Okay? Need to be able to do that. All right. So in summary, we have accuracy and precision. Accuracy says you got the right answer, which you expected to get. Precision says they're grouped closely together. You should understand why we have uncertainty in measurements and when you're estimating that last digit. And you need to understand significant digits. You better have taken notes, okay, because you're going to see sig figs for the rest of the year. We'll see you in class. Ask me if you have questions. Have a good day.